Hello everyone, and welcome to my 7th sequential circuit video. This one is going to be on synchronous counters. And today we're going to be building a counter that can count from 2, 3, 5, and 7, and then as well in the reverse order from 7, 5, 3 into 2, and then from 2 back to 7, and from 7 to 2, like that. So we can start off with our design process here. We're going to start off with a state diagram. And this state diagram actually isn't right because it's missing two things. One, it's missing the reverse order. So here it's showing 2 goes to 3, 3 goes to 5, so on. But we also need arrows going from 3 to 2, 2 to 7, and 7 to 5, etc. So we need arrows going the other way. And then we also need numbers specifying which values of x are going to be associated with each arrow. So in this particular case, we chose to design, as you can see in the next day table, I did incorporate it in here, where if q is 0, then, if x is 0, then we're going to be counting up, and if x is 1, then we're going to be counting down. So all of these arrows going right, or not right, but, upwards, I guess you could say, are going to be x equals 0, and everything going downwards is going to be x equals 1. Alright, so from that design, we were able to make our next state table. And, we've gone over next state tables a million times, so I'm not going to go too deep into it, but basically, we're using JK flip-flops in this one, so we just, when x is 0, we're going to go to 3, when x is 1, we're going to go to 7 from 2. And then from there, you look at our JK flip-flop transition table, and we're able to deduce all of these J and K values. And from here, we make our Boolean equations, which I actually wrote out and created, or K-maps and then Boolean equations, and I wrote all these out. So for J2, it's just equal to Q0. For K2, it's X exclusive or Q1. J1 is just equal to 1 because there are no instances where it is specifically 0. K1 is this kind of long equation here. X and Q2. There might be some Boolean rules that you could use to shrink this, but I wasn't 100% sure, so I decided to, for the sake of time, just go with the more complicated ones. And at the top here, you can see that J1 equals 0, and that's because when looking at J1, I realized making this K-map was a total waste of time. I could have just immediately figured out that it was 1. So I learned from that mistake, and I just, J0's K-map is essentially the same. The ones might be in a different spot, but there are no zeros. You can just say it's 1. And then lastly, K0, kind of similar to the other one. It looks like you could add an exclusive OR here with X and Q2. Again, I just wasn't totally sure whether or not that's allowed, so I decided to just leave it more complicated. Again, for the sake of time, and yeah. So there's that. And then from here, we can go ahead and look at the circuit. This is just the manifestation of everything. So we have our 3 flip-flops. Because we're working with 3 bits here, because we're counting up to 7. If you want to count to 7, you need 3 bits. So here's our X value. So again, when it's 0, we're going to be counting up, and when it's 1, we're going to be counting down. We have this reset port here, in case we ever want to just set everything equal to 0. And then we have all of our Boolean equations mapped out onto logic gates. So we can go ahead and demonstrate. Since X is 0, on every, and all of these are positively edge triggered, on every rising edge, we're going to be counting, 2, 3, 5, 7. However, in this case, you'll see that it actually goes to 3 immediately, and then it kind of goes through the cycle, which is an interesting interaction. Not exactly how sure why that's the case. I'm sure if you really dug into the logic, you could figure it out. And then we can show it counting down. So this is also rising edge. So 2, 7, 5, 3, and it counts down. And in the prompt, it's asking me, you know, actually I can take a look here to make sure I don't butcher the question. It says this particular counter cannot easily be initialized with reset ports. Why not? And it's a little bit of a confusing question in the sense that this reset port does work perfectly fine. So when it says initialized, that leads me to believe that initializing something says that you're setting it to its initial value, its first value. So for example, if you were to initialize a counter going from 2, 3, 5, 7, if you were to initialize that counter, you would set it equal to 2 and not 0. And if you were working with a counter that goes from 7, 5, 3, and 2, initializing it would mean that you're initializing it to 7, or you're setting it equal to 7. And so if that's the case, well, because resetting always goes to 0, you can't initialize it to its starting value. You're always initializing it to 0, which is actually not part of the counter. So that's my best guess for the answer to that question. Let's see here. It also says up and down are just 2 possible modes. Other possibilities could be counted even numbers or cycle through prime numbers. What applications might there be for controlling counter modes? I mean, I can imagine that there's a lot of applications to controlling counter modes. Let's see here. I suppose I can come up with just a very, very out there theoretical, but say that you were doing some sort of NASCAR race. And you know, there's usually the 3, 2, 1, go, right? And then from there, that counter can turn into a stopwatch. So, which will, you know, record the amount of time it takes for the racers to complete a lap, etc. And you could presumably have a counter that can do both things. You wouldn't need 2 separate counters. So that could be like an interesting application. I'm sure you can think of a lot more real-world applications where, you know, you're in a situation where you're using basically 2 different counters, and instead of having 2 different counters, you can just use the same counter in a different mode. So, I mean, the possibilities are endless. So endless that it's actually hard to think of a general one right here. And I believe that is all for today. So thank you for watching this video, and we'll see you in the next one. Bye-bye.